Okay. Okay. Thank you so much, Andrea. Typically, I have been organizing this similar workshop for more than 10 years. I never gave a talk. Since this is a very special situation because we want to support snowmass, I will make an effort to to give also my opinion about different theory for Baryon and Lepton violation. Then my main goal here is to talk about different theories where one can actually understand the origin of Baryon and Lepton number violation. I will not talk about toy models for neutrino masses or things like that. I would like to focus mainly on three main ideas that can actually provide a framework to understand the origin of Baryon and Lepton violation. This is actually my main goal. Then let me start with the basis. The basis are, we have the standard model, and we know that Baryon and Lepton numbers are accidental global symmetries broken only by SO2 instantons processed in 3 units. This is a very important number, 3 units. This means that, in the standard model, we have a well-defined prediction. The proton is stable. Neutrinos are massless. We know today this is wrong. There are no N-bar oscillation, and the only thing that one can expect are delta B equal 3, delta L equal 3 processes, but we know that they are super highly suppressed because these are induced by SO2 processes, and these are processes that are very, very high suppressed, okay? But the standard model makes these predictions very well. Of course, when the standard model was built, neutrino masses were not there, and there are many, many ideas that we will discuss later about neutrino masses. But the standard model makes this very clear prediction. These two symmetries are accidental global symmetry, and they are broken in 3 units. Now, however, often when you go beyond the standard model for many other reasons, you have to think about Baryon and Lepton violation. You have no choice. Maybe the first idea I should mention is, the idea of matter unification, that every time that you write a theory where quarks and leptons are unifying the same multiplet, automatically B and L are explicitly broken because the quarks and the leptons, they are different quantum numbers and you force them to live in the same multiplet. This is the case of grand unified theory like SO5, SO10, where B and L are explicitly broken at the high scale, and generically you predict proton decay, okay? Then this is a hard prediction coming from any grand unified theory. That's why people always believe that maybe the proton is not stable. If you go to one of the main ideas that we have for physics beyond the standard model, for example, supersymmetry, you know that also B and L are explicitly broken even at the renormalizable level due to the fact that you can write interactions that they break the so-called R parity. And this interaction generically also gives you neutrino masses, proton decay, even you can cook model for N-bar oscillation. And also there are theories which are totally different from, let's say, grand unified theory in the sense that you can take, for example, the Baryon number, and the Baryon number can be a local symmetry alone, or Lepton number, or both of them. And in this theory, once you write the minimal version of the theory, you have a prediction that these symmetries can be spontaneously broken in 3 units, okay? As I mentioned, the standard model, SO2 instantons, they break this symmetry in 3 units. This theory also provides a framework to do that. Okay, then if we take the standard model as effective field theory, we knew for a long time that if you write down many high dimension operators which are allowed by the symmetries, the Weinberg operator and the other operator giving proton decay, you can write all of them, the one for N-bar, any other operator. You always can ask this question, what are the values for the scales? Because you want to know which scales are to be able to test the violation of the symmetries. And the only thing that we have is, we have, for Lepton number, if this operator is actually generated, the scale should be below the canonical scissor scale. And if, for example, dimension 6 operator mediating proton decay are there, the lower bound is pretty strong coming from proton decay. However, in general, we have no idea if these operators are there because we don't know how the symmetries are broken. Then, generically speaking, clearly these symmetries could be broken at the lowest scale. Clearly, the Lepton number could be broken at the lowest scale, and we could have a direct access to this mechanism that is breaking the symmetry. And Baryon number, if proton is not is stable, because you don't get proton decay in any theory for physics you understand the model, the scale could be low. All right. Then you know pretty well that for a long time we have been looking for many physical phenomena which can tell us information about how the symmetries are broken. For neutrino oscillations, we know that the flavor Li symmetries are broken. This is something that we learned from the experiment. And at some level, we expect some Lepton flavor violation process that we are still waiting for them, okay? Maybe we will see neutrinos of beta decay, which is very important to see any delta L equal to process. And this is connected to the possibility that neutrino is a Majorana fermion, even if they are, we can discuss more about that. And even if the scale, for example, for Lepton number is broken, if the Lepton number is broken at the lowest scale, you could imagine a colliders, many signals that are consistent with any low energy process that you could hope to see Lepton ovulation collider with process with many leptons. And in the case of Baryon number, we know from cosmology that this has to be broken, and then maybe we get proton decay, and you can have many channels for proton decay, N-bar oscillation, and many other processes that we could imagine. And clearly, so far, the only thing that we have is that we have seen only neutrino oscillation, okay? Now, let me start with the first part of my talk. It's about explicit breaking of Baryon and Lepton number, okay? Then the first main idea in this context, it has to do with grand unification, because we learn from grand unification that we can understand the strong, weak, and the electromagnetic interaction as just different manifestations of the same fundamental interaction at low energy. And in this case, once we unify the standard model in a symmetry like SO5, the fact that we get proton decay as a strong prediction, the relevant scale in this theory has to be very, very high, okay? But how that works for younger people, once we unify interactions and matter, the fact that we put quarks and lepton in the same multiply, in this case in the 5 bar and 10, because we want the anomaly-free SO5 theory, B and L are explicitly broken at the highest scale. And then once you have this, and you check the theory, you check, for example, the gauge interaction, from the off-diagonal part of the gauge interaction, you can actually get contributions, interaction that break B and L, and you get proton decay, okay? And this is a hard prediction. You can compute this very well. And the proton decay is a process where delta B is equal 1 and delta L is an odd number. These are the experimental bounds for proton decay. They are pretty hard. And these tell us that the scale, the relevant scale where you are generating proton decay has to be very, very large, okay? And this is sad in the sense that you're making a hard prediction coming from grand unified theories, but it's sad that everything has to be happening at the lowest scale. But at the same time, you're predicting a new physical phenomenon and allow you to have access to higher scales. Then we know that the original Georgi Glashow model is not realistic because it doesn't even explain the value of the gauge coupling at the low scale. There are problems with the relation between down quark and charged lepton masses. And as was built in the beginning, didn't have neutrino masses. No? But then you can go and take very serious SO5 because it's the simplest grand unified theory that you can write down. And you can add in just a simple Higgs that allow you to have a consistent relation for Fermi masses, for charged leptons and down quarks. You can do very well. You can compute the Gatt scale, you can have unification consistent with low energy experiment, and you can use the matrix element for all these operators and compute. For example, this is the lifetime for the proton, let's say pi0 positron. And in this blue line, this is the prediction coming from the theory. And then you, in this case, there is a new Higgs living in 45 that has to be below the Gatt scale. And you can make very good prediction for proton decay. This red light, dashed light is actually the super K bound. And you can see hyperkamikande could actually prove most of the prediction for in this particular framework. Clearly, here, the spectacular thing is that you can compute this very, very well today with all the information that we have. Then let me show you a second scenario that can actually do even better. We know the matter in SO5 is unified in 5 Baryon 10. And if you want to have a consistent relation for charged fermion masses, you can add Berthollet fermions. And for neutrinos, you can put the 24 fermionic, something that was done by Bias and St. January a while ago. This theory is actually very predictive due to the fact, for proton decay, due to the fact that the Yukawa coupling for aqua is symmetric. This is a renormalizable version of the Bias and January model. And you can compute very well the Gatt scale. And you get, for example, upper bounds on the proton decay lifetime, in particular for the proton decay channel when you have decay into antineutrinos. So after you sum over all the neutrinos, the Wilson coefficient, the relevant Wilson coefficient for the dimension 6 operator, they are actually just a function of low energy parameters. Then you can predict very well. And you can see, you can get a upper bound from the proton decay channels, and something that is always welcome, because if you have a well-given theory and you have too much freedom, it's hard to imagine that you can make a prediction for proton decay in this context, okay? And these are just two examples that I wanted to mention about how well we can predict proton decay in a grand unified theory where B and L are explicitly broken. Of course, we have SO10 and we have other theories. SO10 is a better theory for neutrino masses and in general fermion masses, but it's hard to make better prediction for proton decay. I will not go there because I know Stuart Raby and I think Goran Senjanovic will talk a little bit about that. But clearly we have many interesting theories there that we could use to make a good prediction for proton decay, okay? And then this is the first scenario or first set of theories that we have to where B and L are explicitly broken. And most of all these theories, the grand unified theories, I'm talking about the minima, the simplest things where you can do the best possible calculation for unification. If you can predict proton decay very, very well, they are making a hard prediction and you can actually predict proton decay. Clearly, if proton doesn't decay, we have to forget about the theories, okay? Now, a second set of theories I want to discuss about the explicit violation of Baryon Lepton number is actually supersymmetry. And the reason why supersymmetry, this issue about Baryon Lepton number is so important in supersymmetry is that when we go to the MSSA, we realize that we write the most general superpotential there, and you get the usual Yukawa couplings and the mu terms, but the gauge simply tell you that you're allowed to write down other terms at the renormalizer level. In blue, these are the terms that violate Lepton number, where in red, this is the term that violate Baryon number. And clearly, the gauge simply tell you, and also in supersymmetry, tell you you can write down all these terms. These are the well-known R-parity violating terms. And typically what people do is to impose the so-called R-parity symmetry or study the phenomenological implication of having all these terms, okay? This is very well known that for many reasons, people, in particular, the proton decay, people impose R-symmetry. In this case, people use the lightless neutralino for cold dark matter, but even if the symmetry is broken, you could use the gravitino as a dark matter. Then clearly, this is very important, and the reason why is that if still supersymmetry is playing a role at the TV scale, when I say at the TV scale can be a multi-TV scale, if our part is conserved, clearly when we produce, let's say, gluinos, they will decay down to missing energy, a multi-jet, okay? And this is what you will get. Our parity is a very important symmetry here because it's defining how we could discover supersymmetry at colliders, and also how cosmology could change because the dark matter candidate and even baryogenesis mechanisms could be different. Then in the case of hard parity violation, if I follow this logic, once I produce the gluinos and they decay down to neutralinos, now the fact that baryon number is broken, you can go down to jet. And then clearly the way how we look for this process is very different. In the case of the Lepton number, after I produce my tops and the neutralino, now the neutralino can decay down to same sign leptons and W's, which if you look for the jet coming from the W, you can really look for lepton violation. But this clearly tells you that R parity, and this is very well known for a long time, that R parity is crucial to be able to discover supersymmetry, because all the process can change. We don't really know which is the scenario that is there, and everything has to do with baryon lepton violation, because as I mentioned, these terms violate baryon lepton number in blue, in lepton number, and red, the baryon number. But I have to say that the situation about baryon lepton number in supersymmetry is even more complicated than this, because even dimensional phi operators, these are superfield, the dimensional phi operators in supersymmetry can give you fast proton decay contributions. I would remind you that matter parity is defined by -1 3b minus L, is -1 for all the matter superfields and +1 for the Higgs system vector superfield. And then I will remind you that if you take these two interactions, this violating lepton number and baryon number, you get a pretty fast proton decay contribution. And this is why the reason most of the people assume that they are accent. But in reality, you can put just a bar on the couplings and you can live with that in general, okay? But you don't really know if these interactions are there or not, because everything depends if R parity is conserved or not. Even if you impose R parity and you actually forbid all these terms at the fundamental level, dimensional phi operator for proton decay, after you generate the relevant interaction, you dress this interaction with the Gaussians and all the neutral fermions in the theory, and all the supersymmetric particles, you actually generically get a pretty strong bound for the relevant scale here. The relevant scale here is typically the mass of a triplet living together in grainified theory with the standard model Higgs. This gives you a pretty strong bound, but the fact that you cannot really predict very well this, because you have to put a lot of information in to make a prediction for proton decay, you can actually be consistent with the experimental bound. Now, let me go back and forget about high dimensional operators. Let me focus. I told you these interactions are very, very important because they can change the way how we can discover supersymmetry collider. And the question, how we can understand, for example, have a mechanism to understand the origin of lepton violating interaction in the MSSA, okay? And everything is very simple. The fact that matter parity, if you impose matter parity, they are forbidden, and matter parity is defined this way. Clearly, if you have a theory where B minus L is a symmetry there, you can actually understand the possible origin of this interaction. This is something that was studied by many, many people in the field. And what I will discuss is that if you take the minima B minus L theory, where you just gauge B minus L, to gauge B minus L, you just need 3 copies of the right-handed neutrino superfields to anomaly cancellation. And then you take the theory and you just look at the theory, the different multiplet, and you ask the question, how do you break B minus L? And here, the fact that you are in supersymmetry, you are lucky because this is a super field. There is a scalar field living inside that can get the BEF and break B minus L, and you get the MSSI. But in that process, this is what happens. You can go down to your standard model gauge symmetry after the S right-hand neutrino get the BEF, and the rest is the same. Of course, in this case, you will not avoid the BEF for S neutrinos, but the theory, it gives you, this mechanism provide you a very clear prediction is that you don't get baryon number violation, you get only Lepton number violation, and then you can be consistent with neutrino masses. So clearly, the minimal SUSY B minus L theory tell you that R parity must be spontaneously broken. In particular, Lepton number is broken. And something that is even better than that is that the B minus L and R parity breaking scale are just defined by the SUSY breaking scale. Before breaking supersymmetry, you cannot do that. You cannot give a BEF to the S right-hand neutrino. And if still supersymmetry is playing a role, is there at the TV scale, clearly this is predicting, this has all the nice thing about supersymmetry, plus that this is making a prediction that Lepton number should be seen maybe at the LHC if the SUSY scale is not far away, okay? One interesting thing that for people looking for Lepton ovulation collider is that in this kind of theories, you can predict the electrons through the photon, the Z and the new Z prime, the theory, and they decay to neutralino and leptons, and the fact that Lepton number is broken, the neutralino can decay back to leptons at W, and then you get a jet from the W, and you can get actually very spectacular signals for this collider, and this is consistent with any low energy process. And you can have multi-lepton signals when 3 of the leptons with the same electric charge and 4 jet. You can do the calculation, and here clearly, for example, this is a calculation with only 20 inverse femtobar. But we have, if you have more luminosity, you could start probing part of the parameter space in this case, okay? But this is something that I find interesting because, can open maybe new ways to look for supersymmetry. The Atlas collaboration took this theory very serious, and they did many analyses. Here I will present only one because it's interesting to know, for example, the lower bound on the mass of the stop. And in this case, the stop, decay like a laptop quark. And then they did the whole analysis, and in this plot, you can see this is the branching ratio of the stop to B tau versus the branching ratio of the stop to BE. And they can actually study the whole, assuming a few things, they can give you what is a lower bound. As you can see, the lower bound, the stop here, is like 900 GV. And everything is around 1.3, 1.4 TV. Clearly, often you get the impression that supersymmetry, I don't know, is out because the bounds are very strong. One has to be very careful with that because clearly supersymmetry can be around. There are other issues about the Higgs mass and things like that we can talk, but clearly you are pragmatic about how to discover supersymmetry. Here, for example, the fact that Lepton number is broken, the stop can decay in this way, and then you can see that the lower bound is actually, yes, it can be even below the TV, okay? And then this is, let me emphasize again, maybe supersymmetry is relevant to describe physics at the TV scale, maybe, we don't know. And the important thing is that I show you that generically you have this interaction violating baryon Lepton number, and then this tells you that the way to discover supersymmetry is very different from the usual way, way when R parity is conserved. But I tell you that one can write a simple mechanism where actually R parity must be spontaneously broken, and the relevant scale is just SUSY scale, and maybe we can see Lepton number violation at collider if this is actually true, okay? Then I believe I cover 2 main ideas that we have in physics beyond the standard model, where typically we have to think about the explicit breaking of baryon Lepton number. In the second case, you can do even better because you can actually use B minus L to understand how our part is broken or not in nature. Now I will move to something I particularly find very interesting is the idea of having a spontaneous B and L breaking, okay? Then this idea is very simple. You just, let's say you take the Baryon number and you want to understand if this can be a local symmetry and study the spontaneous breaking of this symmetry. The main idea in the most clear way, I believe, was mentioned by Abraham Pais in '73, and later you will find some papers where people study anomaly cancellation, things like that. But I believe that in this particular, Mark Weiss and myself, we were the first to write the realistic model where this idea can be realized. Actually, we wrote several papers on that. And the idea is pretty simple. Take the standard model and gauge Baryon number. Here you can forget about Lepton number, but everything they will say is similar to Lepton number, but just take Baryon number. And then clearly, as you know very well, Baryon number is not anomaly free. Therefore, you have to understand how to cancel anomaly to be able to study spontaneous symmetry breaking as you do in the standard model. In the case of the Baryon number, you just write down all the anomalies and check all the anomalies. If you take the Lepton number, you will have similar anomalies. In our papers, we put Baryon and Lepton numbers together. There are mixed anomalies. There are many anomalies to worry about, but we were able to cancel all of them in a pretty simple way. But if you think just about Baryon number, in the standard model, there are only 2 anomalies which are different from 0. Then you have to understand how to cancel this anomaly, and then you have anomaly-free theory, and then you can do a spontaneous symmetry breaking. We studied different solutions for that, and today, after the Higgs was discovered, the only solutions that are allowed are using Berthollet fermions, because if you don't have Berthollet fermions, you will modify the property of the standard model Higgs, and this is not welcome today. Then realistic theories that we have kind of 3 different scenarios. The first one has only 4 representation, and the second 6 representation. But actually, they have after symmetry breaking the same degree of freedom, but the structure of the theory is different. And in the beginning, we were pretty conservative. We wanted to use only one Berthollet family. Then let me discuss the one with only 4 representation. You take the standard model and if you gauge Baryon number, you can prove that with only these 4 multiplet, when a well-defined, there is no freedom here. The fact that this is the minimum number of representation that allow you to cancel anomaly. The Baryon number for this new multiplet, which are they have to get Berthollet mass, is actually 3/2 or minus 3/2. Then you can write down all the interaction in the theory, which is pretty simple. And the important thing is that they have electric charge, and they cannot get mass from the standard model Higgs alone. They have to get mass from the new Higgs. And then once you introduce a new Higgs and take into account the Baryon number, the anomaly cancellation tell you that you should have, you find that the new Higgs has to have a Baryon number 3. This means, this is something very, very interesting, because from anomaly cancellation and the generation of masses, you find that you will get delta B equal 3, no delta B equal 1, or delta B equal 2, whatever. This means that the proton is stable. This means that this is a theory for proton stability, okay? I will remind you that in the standard model, the Baryon number is broken in 3 units by SO2 instantaneous. Here, you also break the Baryon number in 3 units, but using spontaneous symmetry breaking. And then the fact that this is the prediction, the hard prediction that is making the theory, the minimal theory that you can write down, this is a gauge theory that tells you that the proton is stable. On top of that, there are many interesting things. For example, in this 4 multiplet, you will find a dark matter candidate, which is automatically, it's a bonus coming from anomaly cancellation. As you know, typically when we study dark matter today can be anything. Here, thinking about spontaneous breaking Baryon number and getting in this process of canceling anomaly, you always find that there is a multiplet that can be dark matter candidate. And of course, you will get a new gauge boson that decay to quarks and the new fields present in the theory. And you get many interesting signals associated to the presence of dark matter. As for example, you get in supersymmetry, many signals associated to that, okay? Now,
Pavel,
yes.
You have a couple of minutes left.
Oh, very good. I am almost done. Now there is a question is that I tell you that you can break Baryon number as local symmetry, and but of course we were talking about ground unified theory where the B is broken explicit at a super high scale. Here, the interesting thing is that if you check the experimental bounds on for the Lepton VC prime, the relevant scale is the mass of this new gauge boson. You will be surprised, but the scale can be pretty low, even around the Lepton scale, okay? Consistent with all the experimental bounds that we have in collider physics and any low energy process or anything that we have, the scale can be actually pretty low. Of course, will be interesting, no? And the fact that the scale can be low, you can study, for example, all the production mechanisms for this Lepton VC prime. I can show you here. And you can ask me later, but clearly you can have huge cross-section for these processes. And this is actually a way to maybe discover something different. Maybe the experimental didn't pay enough attention. Now, something that I mentioned is that in these theories, you always have a dark matter candidate, which I find is fascinating because it's a bonus. It's not something that you were putting by hand. And you can study the dark matter phenomenology. And this is actually very interesting because once you do the calculation, you realize that once you impose the condition that you don't want to overclose the universe, means that you don't want more dark matter that is welcome, the scale for symmetry breaking cannot be high. Typically in a dark matter model, the scale it can be constrained by unitarity around 100 TeV, but here the fact that dark matter is also getting mass from the symmetry breaking, the perturbativity condition, the Yukawa couplings tell you that you have to live below 10 TeV or below in this allowed region here. These are actually collider bounds and you have to live for these cases. You can live in a resonance, you can live in a broad region. But the important message is that collider physics tell you that the scale can be very low, and cosmology will tell you that the scale cannot be too high. And this is very interesting because then you have a theory that can live at the lowest scale in agreement with all the experiments. Then I would like to emphasize the spontaneous Baryon number violation is that the scale must be low. In this, if you take this idea very serious, you see that the minima theory tell you that the scale must be low in agreement with cosmology. Therefore, we can understand the spontaneous breaking of Baryon number at collider. Then let me summarize. In the beginning of my talk, I talk about ground unified theory. As you know, ground unified theory has been there for a long time. But clearly, these are very interesting theory. We're making a hard prediction that's called proton decay. We don't know what is true, but clearly we should keep looking for proton decay and see if we find something. But the only thing I can say that you can write consistent, realistic ground unified theory where you can do pretty well for the prediction on the proton decay. And this is something that we should keep thinking. In this case, I mentioned B and L are explicitly broken once you do unify matter. And I talk about supersymmetry as one of the ideas that we have for physics beyond the standard model. In that case, I told you that the interaction breaking B and L play a major role, which define how we discover supersymmetry at collider, and of course the cosmology as well. And this is often people don't emphasize enough about this, but this is very important for supersymmetry. And I mentioned that if you want to understand these interactions are there using a dynamical mechanism, you can build a simple theory where B minus L is spontaneously broken at the SUSY scale. Therefore, if the SUSY scale is low, you can hope to find Lepton ovulation collider. And finally, I say that if B and L are local gauge symmetries, the spontaneous broken at the low scale, I mentioned that the minimal theory predicts that the proton is actually stable. And on top of that, you get as a bonus that dark matter is there from anomaly cancellation. But the most important thing that I find is that cosmological bounds on dark matter tell you that the symmetry has to be broken at the lower scale. Often we have many ideas for physics beyond the standard model, for example, supersymmetry. We have some arguments to motivate that SUS is at the lower scale, but if you remove these arguments, it can be any scale. Here, the fact that you don't want to overclose the universe, you are forced to live at the lower scale, and therefore there is a hope to think about, to test the theories. But the important thing is that here, these symmetries are spontaneously broken, and I believe this set of theories that I discussed give you a whole overview of different possibilities. And of course, we will have time to discuss other things. Thank you for your attention.
Thank you, Pavel. Any questions, comments from the audience? I have one then. You know, in your first bullet in the summary, you mentioned proton decay could or should be, according to models, at the doorstep of what we can probe today. Now, this is always a tricky thing to say, because then, you know, if you don't find it, then you push the boundary and then you redevelop the theories. How continuous is this sliding bar, for example, for proton decay? So, you know, if we don't find it, then you know, there's models that are tweaked in a way that you can accommodate essentially anything, or at some point things fall off a cliff.
I mean, the honest answer is that it's really very hard to know, right? The only thing that we can do is that, you know, I always think that the experimentalists should look for any kind of process, and they should know, of course, they should take into account the better theoretical ideas that we have. But the honest answer is that clearly, if you improve the bounds, like hyperchemical can improve the bounds, this will provide a way to rule out a set of theories, but this never, I cannot say that you will rule out all the theories, because in most of these theories, sometimes you have enough freedom to accommodate the experimental bounds. In the cases I discussed, these are really the simpler theories that you can write down realistic, and then at least you can rule out some of them. But the answer to you is that we cannot be sure. Experimentally should look for proton decay and see if they find something. I don't think you can rule out the idea of priming 5 theory if you improve the bound in one order of magnitude or something like that.
Thank you. There is a question from our audience by Perez put. In the case of supersymmetric SU5 times U1, are the bounds for proton decay stronger?
Well, if the person is talking about flip SU5, because, you know, when you talk about unified theory, this is not a unified theory. Therefore, often people talk about SU5, flip SU5. In the case of flip SU5, there is more freedom, the bounds are less strong. But the flip SU5 is not a grand unified theory. It's not a unified theory as SU5 or SU10. Therefore, it's not a surprise that there is more freedom. And in particular, when supersymmetry, there is even more freedom. Therefore, I would say there is much freedom there, and you can accommodate experimental bounds.
Thank you. I guess there's no further question. I suggest we keep the Zoom. Actually, there is a question, maybe.
How do I ask a question? I don't know how to raise a hand.
Yeah, you just asked. Go on. Go ahead.
I did. Okay. I just want to sort of agree with Pavel, but make it a little stronger when it comes to grand unification. There is one predictive theory, or there was, minimal SU5, and it failed badly. Everything else is totally unpredictable. in a sense that you can't know the scale. The threshold effects are just killing you, whether it's minimal supersymmetric SU5, minimal SO10, whatnot. I mean, we have to be honest. I'm going to comment on that so in my talk, but I think since Pavel talked about it, I think it's a good point to emphasize, which is sort of a tragic aspect of grand unification.
All right. Thank you,
I
Gordon.
kind of agree more with you.
Good.
Very good. All right, so let's keep the Zoom room open, but this is a break now. 10 minutes. We'll be back actually at 11 with a session on neutrinoless double beta decay with a theory and experimental talk. I will actually go and make my own coffee. Here I am.
Good.
I don't know, some of the panelists were suggesting to, during coffee break, to allow people to talk. Feel free to talk and discuss anything.
Pavel, I have a question for you.
Oh, yes, please.
So, are there significant bounds from the neutrinoless double beta decay on your spontaneous operator violation for the leptonic sector for this for the neutrino valve?
Yeah, very good. Thank you. If you think about what you get when you have a spontaneous breaking of R parity, you get a theory that is MSSA plus, let's say, bilinear R parity violation in the language that people use.
Right. Right.
And then typically in bilinear R parity violation, you can accommodate very well neutrino masses, and then bounds from neutrino super decay are not very strong. Because the bounds are strong when you have trilinear R parity violation, but the fact that the superpotential has dimension 3, and once you impose B minus L, they are forbidden. After symmetry breaking, you generate only bilinear terms. And these bilinear terms are, once you impose the neutrino bounds, the usual type of SUSY CISO mechanism, these bounds are the most important one. Once you check the prediction for neutrino beta decay, you don't get any additional bound that is stronger than the neutrinos. Then the answer is the most important bounds are the neutrino mass constraints, and you don't get any extra bound for. And you have the usual contribution for neutrino beta decay, but here you have right-handed neutrinos, and you have some extra contribution, but these are, you know, suppressed by mixing and things like that. Then the answer is no. Once you impose the neutrino bounds, you can satisfy any neutrino beta decay bounds.
I see. I thought this bilinear term could be rotated away by proper definitions of your field.
Well, yeah, this was a discussion a long time, but this is true only in the naive case when you take only, here there are different bilinear terms, okay? It's different, and they are, you know, they have the extra-handed neutrino. This discussion about rotating away was just in the pure MSSA, right? That was a while ago in the early 90s. The people like Hobby Haber and things like that.
Yeah.
But in this case, no, you cannot rotate away. You have, you know, more fields. You have right-handed neutrino, the extra-handed neutrinos. But I am using a simplified language. When I say bilinear terms, I have the usual bilinear plus other terms. For example, the bilinear terms is proportional to the back expectation value of the right-handed neutrino. It's something that has to be there because you have to break B minus L. But the important thing is that if SUSY is there, which, you know, I don't, many people are very sad about supersymmetry. I always think that we don't really understand how SUSY is broken, and we should be a little bit open mind. Yeah. Even if the issue about the Higgs mass is painful, because to get a 115 GeV mass for the Higgs, you have to work a little bit. But I mean, supersymmetry could be there.
Yeah. Well, I got a question that might even be related to that. In your concluding slide, your second point was about the prediction that our parity violation has to be part of supersymmetry.
Okay, very good. What I want to say is that, let me see if I open again my file here. What I said is that, okay, let me share. What I said is that in general, we don't know if our parity is broken or not, okay? And clearly, this is very important because it can change the way how we discover supersymmetry, right? But now what I said is that if you ask the question, how do you understand if this symmetry is or no, it's good to find a mechanism for that, right? And then what I said is that the simpler theory that you can write down is just B minus L theory. You gauge B minus L before symmetry breaking. These symmetries these terms are forbidden. Therefore, you take the theory before I break B minus L, these couplings are forbidden. B minus L is conserved. Mar parity is just conserved, and therefore the prediction that this theory is making is that once you want to break the symmetry, there is in the minimal theory there is only one way. Is that the super partner for a Hamming neutrino has to get the background expectation value. Therefore, you will get always R parity violation, but you don't get proton decay because the only thing that you break here is actually Lepton number. At the renormalizer level, you will get only supersymmetry plus Lepton violation. And what I wanted to say is that the prediction is that you should, the minimal theory where you understand the origin of this interaction, tell you that you should have supersymmetry plus Lepton number violation, no Baryon number violation at the renormalizer level. And then this will change completely the cosmology and the collider physics because you will get, sense-sign leptons and all the supersymmetry particles, they will decay way back to the standard model. I don't know if I answered your question.
Oh, I think you're getting at it, but my takeaway in the past has been to avoid ultra rapid proton decay, you had to invoke our parity.
Right.
You're saying you don't invoke it. You may just set one coupling constant to 0 or near 0.
No. What I said is, at least in the context of the B minus L, after symmetry breaking, you don't get Baryon number violation. Therefore, at the renormalizer level, there is no operator mediated proton decay. To get proton decay, you have to break Baryon number in 1 unit and Lepton number in odd unit. After B minus L breaking in this supersymmetric context, you don't get Baryon number violation. Therefore, the proton is stable. You get only Lepton number violation, which tell you that you will generate Majorana neutrino masses and all the phenomenology related. Then you don't get proton decay from a spontaneous B minus L symmetry breaking in the supersymmetric context. Therefore, you are safe. You don't have to worry about proton decay. This was always the motivation to impose R parity by hand to forbid proton decay. Here, you don't have to put by hand. You will break spontaneously B minus L, but you never get proton decay in this context at the renormalizer level. There are high dimensional operators that will give you proton decay, but they can be suppressed because they are coming from the high scale, not from the SUSY breaking scale.
Okay, I think that's clearer.